Hello guys, I'm going to talk about my recent submitted paper to ICOES 2016. Thank you. That paper is about to use fractional order controller in drone. In this way, we can help drone to track a visual landmark. This is a problem. The GPS-based navigation accuracy needs to be improved. Therefore, we put a visual landmark. You can see the red circle on the ground. In this way, we put a camera on the drone. On the right is a view from the drone. You can see the red circle in the camera. In this way, we can get the position information from the camera. We use image processing algorithms to get the relative position. In this way, we can help the drone have a more accurate position control. These are the contributions of this paper. We have put an onboard vision processing system to the common UAV. This is because we have the open source hardware that is Android and open source software. Therefore, that image processing controller can be put on a common UAV. Use a fractional order PID controller to control the UAV. In this way, it can fly more robust, especially in outdoor environment with gas disturbance. We discovered that fractional order PID controller has a better resilience against a large sampling period. This may be the first time. Let's see the system structure. The drone is from 3DR. The autopilot is Pixox. Then we put an Android, which is the white box. The Android has an Ubuntu operating system. We connected the Android to a Pixox with an FETI cable. We also connected the Android with a Wi-Fi module and a camera. We have established a Wi-Fi hotspot on the ground. In this way, we can use the ground station laptop computer to connect the drone via traditional telemetry and the Wi-Fi. We can use the ground station to see the real-time flight data from the mission planner, and we can use Qt to log into the Android operating system to code and start the commands. We can also use the browser to look at the real-time image. We have developed a small app that can tune the red detection threshold real-time. This is the software log diagram. After the Android is powered on, the camera is initialized. Then we can use the image to detect the red circle. We can get if the red circle is in the view. If the red circle is detected, we can get the position. Then the drone will check if the drone is in guided mode. If it is in guided mode and the object is found, then the position information can be put into the controller. The controller can calculate the velocity. Then we use MarLink proxy to send the command back to the drone. In this way, we have a control loop. This is the control block diagram we extracted from the system. This is the position control system. In this way, we have position feedback. Then we calculate the error, put the error in the controller. The controller can calculate velocity. Then we put the velocity to the plant. The plant has two parts, the velocity loop and the integrator. The velocity loop is a first order element. The integrator is a physical velocity to position converter. That is the drone. If the drone has a speed, you can see the position. We use the system identification method in MATLAB to get the model of the velocity loop. In this way, we can get the transfer function of the plant. From these Simulink blocks, we can have an overview of the fractional order PID and integral order PID. This is a plant. We just system identified. There are some parameters we can change. The next step is to tune the integral order PID to get the optimal parameters for integral order PID. Use the MATLAB PID tune toolbox to get the best parameters. This is the parameters we got. From the transfer function, we can get the phase margin and the crossover frequency. In this way, we can use the phase margin and the crossover frequency to calculate the fractional order parameters we want to have. The first, totally we have three equations. The first one is to calculate the crossover frequency. The second one is to make sure the derivative at the crossover frequency is 0. The third one is to get the gain crossover frequency. You can see the both diagram. Here we have plotted both fractional order PD and integral order PID controller transfer function on the both diagram. You can see at the crossover frequency, the fractional order PID has a 0 derivative. That means if the plant model change, the crossover frequency will change. If it is changing, the phase margin cannot change much for fractional order PID. However, for integral order PID, if the plant change, the phase margin will get worse. You can see the transfer function of the fractional order PID. We have simulated the step response. You can see the fractional order PD controller has a better step response. We also investigated the robustness against speed model gain variations. This is investigated by simulation. You can see we have changed the gain by decrease and increase. For the fractional order PID, the blue one is the original one. You can see the result. For both decrease and increase, the step response didn't change much at the overshoot. But for the integral order PID, you can see the overshoot appears. In this way, in terms of the robustness against step model gain variations, the fractional order PID is better. We also done the similar investigation for the time constant tau.
Yeah, this is somehow interesting. So you got a tau 50 plus or minus 50% variation for the nominal tau.
Yes, we have got a similar result. You can see the overshoot for IO-PID controller is more than the FO-PID controller. After we got the calculated fractional order PID controller transfer function, we have to implement that controller in the practical system. Then we should convert this into something we can implement. We use the author loop approximation method to convert this guy to a high-order integral order transfer function. In this way, we can implement that. We also need to transfer the continual controller to the discrete system because we need to use a digital controller to implement that.
Yeah, this is new, totally new. Okay.
Yes. For this part, we tried different sampling periods. If we use large sampling periods, the integral order PID can get much worse performance. If we use a small sampling period, the fractional order PID and the integral order PID can have similar results. In this way, we can say fractional order PID have a better resilience against large sampling periods. We also done some real tests. The fractional order controller has a nearly 20% better performance compared to integral PID controller. These are the conclusions. A fractional order proportional derivative controller for Quad-Rotor UAV vision precision serving. We show that the fractional order controller has a better robustness against the model changes. We discovered that fractional order controller can tolerate larger sampling period. Thank you.
Okay, very good. I will show this the black dot circuit. Do you have statistics? Oh yeah, you have 30% smaller. Okay. 20%.
Yes. I can also show you the. This is a small app we developed to tune the threshold. If the drone is flying in the sky and it sees the red circle, and then we can click the tune and the tuned parameters will go into the input box. Just click the submit button. The thresholds will go into the drone. In this way, we can tune the threshold online.